It's time to investigate yet another force. In this video, we will be looking at weight and apparent weight. Let's begin by examining the differences between mass and weight. Mass is a property of an object that describes that object's inertia, and it's basically a measure of the object's tendency to resist any change in motion. Mass is measured in kilograms. Weight, on the other hand, is the gravitational force acting on an object. So this is a vector that can be calculated by multiplying the mass times the gravity. Notice that it is negative because weight always points downward. Weight is measured in kilogram meters per second squared, or better known as newtons. By now you should be familiar with the idea that for any object resting on a surface, the normal force is the force of the surface pushing back against the weight of the object. Now your weight is the force pushing downward. However, what you feel is actually the normal force, or what is pushing back up against you. We can now define the concept of apparent weight as the magnitude of the supporting contact forces acting against an object, which of course is usually the normal force. Let's look at some examples of how the normal force can change. In this first example, the weight down and the normal force up are equal. So either this object is at rest or it's moving at a constant velocity, but regardless, its acceleration is zero. Because of this, we know that the normal force is equal to the weight. In this next example, the elevator is accelerating upwards. Now that doesn't necessarily mean it's moving upwards. It could be moving downwards and slowing down, in which case the acceleration would point up, or it could be moving upwards and speeding up, in which case the acceleration would once again be pointing up. But regardless, the acceleration is upward. Because of this, there must be more force going up than there is going down. And therefore the normal force is equal to the weight plus mass times acceleration. Another way of looking at this is that the apparent weight will be greater than the weight. And so if you were standing on a scale in an elevator doing this, the scale would read more than what your actual weight was. In this example, the elevator is now accelerating downwards. In other words, there must be more of a downward force than an upward force for it to accelerate downwards. Because of this, we can see that the normal force must be less than the weight. In fact, the normal force is equal to the weight minus mass times acceleration. Or the apparent force is now less than the weight. If you were standing on a scale in an elevator doing this, the scale would read that your weight was less than what it really was. In this chart, we will summarize the different conditions for motion on an elevator and the apparent weight. We will look at these three different original motions of either the elevator being at still at the beginning, velocity equals zero, the elevator moving upwards at the beginning, or the elevator moving downwards. For the first condition of the elevator being at rest at the beginning, and there are three different conditions which could occur. First, the elevator could remain motionless, in which case, of course, the acceleration is zero, and the apparent weight is just equal to the weight. In other words, the normal force is equal to the weight going down. In the second condition, an elevator at rest could begin to move up. In that case, the direction of the acceleration is upwards or positive, and the apparent weight is equal to the weight plus mass times acceleration. In other words, you would feel heavier. In the third condition, an elevator at rest could begin to move downwards, giving you a negative acceleration down. In that case, the apparent weight would be less than the actual weight, and you would feel lighter. If the elevator is already moving upwards, one of two things could happen. Either it could speed up or slow down. For it to speed up, the acceleration would need to be positive or upwards, and for it to slow down, the acceleration would have to be in the opposite direction or downwards. For each of these, we see that the apparent force is either more than for a positive acceleration or less than for a negative acceleration, whatever the original weight was. If, on the other hand, the elevator is already moving downwards, then just the opposite occurs. For an elevator moving downwards to speed up, it must need a downward or negative acceleration and a positive acceleration for it to slow down. Therefore, the apparent weights are just the opposite of what they were for an elevator moving upwards. Now let's look at a problem that involves apparent weight. Angers is standing on a scale in an elevator that's moving, and as the elevator comes to a stop, the scale reads 750 newtons. Now, they want to know, was the elevator moving up or down, and how long did it take to come to rest? Well, we can begin by looking at some known values here. We know the apparent weight is 750 newtons, and we also know that Angers' real weight from gravity is 686 newtons. We can draw a force diagram that shows that the apparent weight of 750 is more than the real weight of 686. That sort of lets us know that the acceleration was positive. We can actually find out what the value of the acceleration was by equating the normal force to the weight plus mass times acceleration and solving through for acceleration. Now we can answer the first question. Because the elevator is slowing down, but we have a positive acceleration going upwards, then the acceleration must be in the opposite direction of the original motion, and the elevator was moving downwards to begin with. With a value of 0.91 meters per second squared for acceleration, we can use our kinematics and find how long it took for this acceleration to occur by solving for time. That concludes this video on weight and apparent weight. Tomorrow we will work some problems along these lines and begin looking at my favorite section of the library, friction.